It's fabulous to be back in Cambridge, so thank you very much to the organisers for giving me this opportunity to. All good?
Yes, no.
Fabulous. Giving me this opportunity to tell you about primordial nucleosynthesis and the search for new physics. So my task is to tell you about Big Bang nucleosynthesis to a community of people who probably don't think about this every day. So give me one slide to introduce you all to Big Bang nucleosynthesis, just in case you haven't come across it before. It's the product of putting neutrons and protons in an expanding universe and seeing what happens. So when the universe is very young, about 1 second old or thereabouts, protons and neutrons are roughly in equilibrium, but some of those protons and neutrons are combining to form deuterium. As the universe expands, it gets cooler and the density drops a little bit. And these are sort of the two key parameters, how much the universe is expanding and the density of the reactants. And as this process continues, more and more deuterium is made until effectively all of the neutrons end up in helium-4. And at this point, helium-4 freezes out. And after about 1 Earth day or thereabouts, the primordial abundances don't change by more than 0.1%. So it takes about a day for the most common BBN nuclides to freeze out. Unfortunately, I don't have a day to tell you about it. I've only got 10 minutes, probably 8 minutes now. But I wanted to focus on one particular nuclide that's made, okay? And that is helium-3. And the reason is because it's extremely hard to measure. It's only been measured in the Milky Way. And previously, helium-3 has been detected and measured in the Milky Way, but it usually requires a lot of modeling assumptions, it requires an ionization correction, and only the best systems are allowed to do this. So let me first give you a summary of what people have done in the past. So an absolutely heroic effort by a trio of people, Bania Rudenbolsa. They spent 4,800 hours, that's 200 days non-stops, or for the X-ray community, that's about 17 megaseconds of information. This is probably the deepest centimeter wave spectrum ever obtained, which I think is a real testament to this heroic effort that they've done. This is the helium-3 plus line they were looking for. This is the same as the spin flip transition of H1 21 centimeter, but for ionized helium-3. Okay, so after a bunch of assumptions, you crank out a number. Here's a follow-up study by the same group of people, and this is their 5 best systems. Okay, after the heroic effort of 59 different systems they observed, they went back and did the 5 best. And this is what they found. So the data points here are measurements that they constructed of the helium-3 abundance in the Milky Way as a function of galactocentric radius. Now, the red line is a galactic chemical evolution model, and this galactic chemical evolution model is not tuned or tweaked to the helium-3 abundance measurements. It's tweaked to things like the abundance gradient of the Milky Way, the vertical disk scale height, the star formation history, things like this, independent of helium-3. And so overall, it agrees pretty well, and the standard model BBN is this line, roughly here. Okay, and so helium-3 is produced in the Milky Way by stars, but it's produced only at the level of like 30%, 40% above the primordial value. So we're still pretty close to primordial in the Milky Way. But as I mentioned, these systems require, which are H2 regions that people have observed, they require a lot of modeling assumptions, ionization corrections, so we wanted to try and go back and do this a bit better. Now, what I'm going to tell you about is the helium isotope ratio. So this is the relative abundance of helium-3 relative to helium-4. These are both primordially produced. The benefit of helium-3 and helium-4 is that they have very similar ionization potential. So there's very little that can go wrong in terms of ionization corrections. Things are also very similar because they basically have the same ionization structure. Now, another thing that's really neat about helium-3, the helium isotope ratio, is that these 2 parameters I told you about with Big Bang nucleosynthesis, this expansion rate, which is parameterized by N effective, and the baryon density, that's the density of the reactants in BBN. What you see here, the gray is CMB, the blue is from deuterium, which is the hydrogen isotope from BBM. And helium isotope ratio offers orthogonal bounds to deuterium. So in principle, high precision measurements of the helium isotope ratio and the hydrogen isotope ratio will give you great constraints on N effective, which is the expansion rate, and the baryon density. So that's the goal. So how did we do it? We went and observed one of the most popular astronomical objects. You may recognize this as the Orion Nebula. And we observed this star, which the arrow is also pointing to, so you don't need the laser pointer. And that's one of the brightest stars in the Orion Nebula. Okay, this is like a 5th magnitude star, and we went and observed it with the VLT. We went and observed it for, thank you very much, it's perfect. We went and observed it for 30 minutes, okay? 5th magnitude star for 30 minutes at the VLT, and we got these extremely exquisite data, okay? This is signal to noise of over 1,200 at a spectral resolution of about 3 kilometers per second. This is an extraordinary data. And what you have here is an absorption from metastable helium-4. This is metastable helium-4. And this is because the spins of the two electrons in a helium atom are aligned. And that's the only way you can produce these metastable helium absorption lines. So there's basically this screen of absorption in front of the Orion Nebula that are producing these metastable helium-4 absorption lines, these really strong lines. Now shifted by about 36 kilometers per second, I've got a zoom in here, this is the corresponding helium-3 absorption line. And it's only revealed at these really high spectral resolutions and really high signal to noise. So combine all this information with optical data as well of helium-4 absorption lines, and we can get a helium isotope ratio measurement. And this is what we've just done to prove this technique can work, and we can push this to more metal poor environments. So this is what the previous status was. Our measurement falls here. So not only is it higher precision than has been achieved before, but it's also roughly in agreement without any tweaking with this galactic chemical evolution model that we had previously obtained. So what can we learn from this? Well, one thing we can do is we can try to back out what the primordial value might have been, given that helium-3 has only been produced above the primordial level by about 30% above the primordial value. And so what we take here is a measurement of the helium isotope ratio of Jupiter, which is the sort of the pre-solar value of the helium isotope ratio of our solar system, and our measurement of the Orion Nebula. And we try and construct a galactic chemical evolution model that allows both of these measurements to give a consistent value of the helium isotope ratio at time 0 for the Big Bang. Now we find a disagreement here which is about 2 sigma, but this hasn't got any systematics or anything associated with some of the modeling uncertainties. And so I think this is incredible agreement, given that we only have one measurement and that we can push this with future observations, we can produce a lot more measurements. I think this is actually a real big testament that we now have so many primordial element abundances, which I haven't mentioned today, but we have deuterium and helium-4 and helium-3 isotope ratio, and they all agree with the standard model at better than 20% precision. And that's a statement that I think will hold true. Some of these are much better than 20% as well. Some of these are at 1%. So I think that this is becoming increasingly difficult to explain this primordial lithium problem, this cosmic lithium problem, which I haven't mentioned, I won't mention because I'll undoubtedly be asked about it in questions. It's becoming increasingly hard to understand this as deviations from the standard model. But I think one future direction that we can go in is to continue measurements of the helium isotope ratio. We've now increased the number of metastable helium absorbers that we know of in the Milky Way by over an order of magnitude. We now have about 50 absorbers that we now know. And we are confident that we can get helium isotope ratio measurements from these. We've had incredibly bad luck with VLT. So unfortunately, I have got no new results yet, but stay tuned because we will have some next year. But we know the sight lines to go after. What's more, and I think this is a really exciting thing for the future, talked about the past, let's talk about the future. In the next decade or two, I think we'll get a great opportunity to measure the primordial helium isotope ratio. And the way I believe we can do this is with gamma ray bursts. Here is an example of a spectrum from one gamma ray burst where metastable helium absorption was detected. It's unresolved. And it's at relatively accessible redshift. So this is a redshift of 0.9 or thereabouts. But these are in more metal-poor environments than we have in the Milky Way. And more importantly, they're at earlier cosmic times. And helium-3 is primarily produced by low-mass stars. And so getting these at an earlier cosmic epoch actually means you're more likely to get closer to the primordial value. So this is a really exciting thing, and I'm confident that Andy's with the ELT will do this. Okay, just to summarize in my final minute, one of the things I mentioned was that Big Bang nucleosynthesis agrees remarkably well with the standard model. On the top here, you can see this is helium. The helium mass fraction, or helium number abundance in this case, agrees well with the standard model. So these curves you can see here, these are the standard model curves. This band here is the observations, and CMB is this gray band. So all of them intersect. That's a really good thing. There's an intersection. This is deuterium, which agrees remarkably well. Helium isotope ratio and helium-3 abundance, all upper limits. And then you've got this thorn in the side of BBN, which is lithium-7, but we're becoming increasingly confident this was probably a problem with stars. I reported the first measure of the helium isotope ratio in an extrasolar environment, and future measurements are upcoming. One of the things I didn't mention, but I thought was really interesting to point out to members of the audience who might be interested in the Milky Way chemical evolution or simulations, I think that the helium isotope ratio, if we can map it as a function of galactocentric radius, it's a great chance for us to understand the relative importance of inflows of mostly primordial gas and outflows of mostly enriched gas, because helium-3 and helium-4 are produced both primordially and by stars. So this offers us a great opportunity to understand the relative importance of inflows and outflows in the Milky Way. Finally, I think future telescopes will allow us to measure this in a near pristine environment, and this will give us the real first solid measurement of the primordial helium isotope ratio and allow us to study BBN in increasingly great detail. And thanks for your time.